Here real quick with just like an integration summary. So again, it seemed like on the test sometimes we're having trouble deciding like what do I do with this, because you're giving me like a different presentation than maybe this other time, and then it's a different presentation from that time, and like what am I looking to do here? So if you have a definite integral, if you're looking to calculate a definite integral and you're given an equation, you can compute an antiderivative and then use the fundamental theorem of calculus part 2 to plug in the upper and lower bounds and take the difference. Now, one of the most common mistakes I saw in the test was people not computing an antiderivative and just plugging it in to the function you're integrating. So like I saw a lot of like, if you had the integral of x dx from 1 to 2, just plugging 1 and 2 into x and not the antiderivative of x. Do you guys, when I say that, is the vocabulary okay? Okay. So again, be careful about that. If the directions call for an exact solution, it must be done with an antiderivative and then plugging things in by hand. If it asks for an approximate or rounded solution, your calculator could do that. Your calculator should be able to handle that, right? We've shown you how to use the integral function on your calculator to do definite integrals. The one place to be careful is if it's an absolute value. If you have the absolute value of a function, you have to figure out where the function changes from positive, negative, and then like chunk it into positive pieces and negative pieces. And then all the areas that you're computing need to be positive results. So whether you make an absolute value of your answer and make it positive, or you just do negative of the integral, or whatever, however you want to do it, just everything coming out of that has to be a positive area, right? So if your function is given to you as a graph, and you can geometric up the graph, like chunk it up into rectangles or squares or circle pieces or whatever, you can use geometry formulas and calculate areas under the curve and approximate, or actually get an exact value for your integral that way. If it's curved and all you have is a graph, well, you can use a Riemann sum to approximate the area under the curve to get an approximate value for that definite integral. And if you're given like a table of selected values, the best you can do is do a Riemann sum approximation, right? Just like break them up into rectangles, and best you can do without like them telling you that, some other information about what the function behaved like. But in general, that's the 3 presentations you'll get. Your function as a equation, as a graph, or as a table of values. And if we're talking about integrating that function, it's going to be kind of like one of those techniques, right? I don't know if that helps to kind of see it all in one place, but it felt like as I was looking at things, I'm like, spend 5 minutes and kind of like lay this out and put it in one place and just kind of have a conversation about what to do here. Okay. On Thursday last week, I was absent. I left you a video lecture of what we're doing. This is a challenging topic. Did we watch the lesson? Okay. Attempt some homework? Okay. Less on that end. Some of us yes, some of us no. That's okay. Do you remember the idea? What were we doing in section 6.2? What was the main idea? Great. We're trying to calculate the volume of an irregular shape, something that's not like one of these solids like we would have seen in either circular solid or rectangular solid like we would have dealt with in geometry, right? So like if we have, something like this, right? And we're asked to find the volume of this shape. Woof, there's no volume formula for that thing, at least in geometry land. But what we decided to do, or what the calculus idea would be, is we're going to just kind of like slice this thing into really thin little slices. So what you're getting is like one little tiny cylinder for each slice. If you slice that thin enough, even if it's like changing sizes, if I take a thin enough slice, it's going to become like a regular cylinder where the area of the base are approximately the same, right? If I do that slice infinitely thin, they have to be the same, right? So now it's a cylinder or a rectangular solid or whatever, right? It's a geometric shape. So I can just do area of the base times the height. And if I add up the volumes of those infinite slices, I have the volume of the figure, right? So that was the idea, right? Was that our volume was the integral from a to b of a of x, which is our area function of the cross section, and then the dx is like the height of our cylinder, right? So this is like area of the base times the height, right? Does everybody feel okay conceptually with kind of what we're doing? It's important because the concept really kind of dictates the method that we're going to be using here, and a lot of the intuition that we need for like coming up with the measurements and how to set up the problem really help if we have a good understanding of kind of like what we're trying to do. Beck.
Can you explain the dx being the height? Because doesn't the dx go away when we take that integral?
Right. So remember, like, that this is like the limit as n goes to infinity of the sum I equals 1 to n of f of x I delta x, right? And when we do this as a sum, like the delta x is a number. It's now just becoming infinitely small, but that's the same as like the height for our cylinder, okay. Like our area formula for our cylinder or whatever, or rectangular solid or whatever, it's whether it's a box or pyramid or whatever. Okay. But that's the idea. It's like this all comes back to remember what we're doing is we're adding up like infinitely many of these rectangles. And in this case, since it's a three-dimensional shape, now it's instead of it, the rectangle, there's the delta x being the width of the rectangle, it's the width of our cylinder, basically.
Okay.
Does that?
Yeah.
Okay. So we're taking that same idea to do that. Now, like if our cross-sectional area is a circle, it's going to be pi r of x squared, right? Where the radius is going to be written in as a function in terms of x or y or whatever. If it's a triangle, it would be like 1/2 b of x times h of x, where b of x is our function for the base of the triangle, and h of x is our function for the height of our triangle. If it was a rectangle, it'd be like L of x times W of x, like width of x. So all of these measurements for these, like dimensional measurements for these area functions are going to be functions of x, right? So the radius is not going to be like just a number. It's going to be a function of x. The width or the height, not just a number, it's going to be like a function of x. Does that feel okay? Yeah, go ahead.
So if the height is the geomet's, why do we have height in the triangle?
So a height, okay, repeat your question again. I think we're just having like a communication issue.
Height is the geomet's.
Okay, so like, yeah, so like, think about what we're doing is like, we're basically, we have something like this. Right? So this is like the height for the figure. That's what I mean by height for the triangle. Because we're talking about the area of a base. Excuse me. You catch the... Yeah, okay. I thought that was what the issue was, but I need you to repeat it just to make sure. Okay. Okay. Does everybody feel okay with the concept of kind of what we're trying to do? All right. Let's do some of the stuff from the homework, right? Ideally, you would have started some of this, maybe tried a couple. But let's work through some of these homework problems today. I'll do like the first one or two here as a sampler and just kind of ask for some feedback from you guys, and eventually we'll transition to like give you guys some time to work on one, and then we'll go through it together and try to feel like we could feel good about this and build some intuition. Sound good? So I would encourage you, if you aren't a usual like note taker, this is something we're probably going to want to like participate in at some point. So I'd have something out to write on, whether it's in your OneNote or if it's on a sheet of paper, whatever is okay with me. But this tends to be one of the trickier second semester ideas or second semester problems, because the setup is really the trick, right? Once you have the integral written, usually that goes pretty well. Worst case scenario, you can always default to using your calculator to make sure your setup is correct, right? Like you can take your setup and just type it in your calculator and do the integral and check the answer to make sure it matches before you start trying to integrate something that's not set up correct. All right. Let's look at number 1, right? I think I assigned, what was it? It was 1 through 11 or something, and then something and something. Let me grab it from over here. Okay. Oops. All right. Bless you. No problem, dude. Oops. Grab that real quick. All right. This says, find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. Sketch the region, the solid, and a typical disc or washer. All right. So let's see, we're looking at the region, it's bounded between y equals 0, which is the x-axis, the vertical lines x equals 1 and x equals 2, and then this is the curve, right? What kind of a function is y equals 2 minus 1/2 x? It's a straight line, right? It's a linear function. So the values that I'm going to plot to get a picture of this are going to be, I'm going to use 1 and 2, right? Because that's going to tell us where the part that I care about, which is just between 1 and 2. So here I get 1.5, and there I get 1. Everybody cool? So let's draw our picture here. So I'm going to go by half. Every box is going to be a half unit. So there's like 1, and there's going to be 2. So I have 1 and 1.5, so 1, that's a half, 1, 1.5, and then 2 and 1, so 1 there. So that's my shaded area. Does everybody feel okay with that? Now if I rotate that about the x-axis, we're going to be rotating about the x-axis. What am I going to end up, what's this thing going to end up looking like? It's going to look kind of like that. Isabel? So we have like, let's do this. I have like this trapezoid piece, and we're going to rotate it about the horizontal line. So like that area or the space that I just traced over is all a solid now. That's what it means. So like that's what I'm trying to picture in my mind. So I'm going to close my eyes, use my imagination, and think about what's happening here. So like this part makes like a circle with that radius, right? As it spins around. This part makes a circle with that radius, spins around. And because this is flat, it's going to be like a smooth, straight. So it's like part of a cone, right? It's like a cone with the top chopped off. Does that feel okay? Yeah. Sure. So that's like what my solid would look like. Does everybody feel reasonably okay with that? So if I think about this, oops, let me do that. This is still like my x-axis here, right? So if I take a slice through that, I'm going to be slicing so that, do I want to be slicing vertically or horizontally here? Vertically. Why do I want to be doing vertically and not horizontally? Because I want all my cross-section shapes to be the same shape. They don't have to be the same size, but they need to be the same shape. If I slice this way, you're getting all kinds of crazy looking things, right? If we slice this way, though, everything that we slice is a circle. Does everybody feel okay with that? Okay. So let's now sketch that cross section. So I'll draw one of them in there to kind of remind ourselves what this is going to look like. All right. So here is the x-axis, right? And one of my cross sections is going to be like a circle, right? So this spot here is going to be just some arbitrary x value, right? Does everybody feel okay there? And this will be our radius. So if I translate that to here, that's like my arbitrary x, and that's like my radius, right? Can everybody kind of see that? That the line that I'm going to be rotating about is going to be like the center of my figure, right? The distance from the line that I'm rotating about will be like the radius of the figure, right? Or of the cross section in this case. Can you guys kind of picture that in your heads? Again, if you need to close your eyes and like try to clear your head and use your imagination, that's normal. Like much of the time I spent doing these problems when I was first encountering them was me just trying to like get a good picture of what this thing looks like so I can set up the problem correctly. Like it's not wasted time to try to get good at being able to do that. It's a very helpful skill, and I don't know a better way of doing it other than like trying to clear your mind and see something in 3 dimensions, which for some of us it comes easy. That'll come easy too, and some of us it'll be a real challenge. The good news is that they're all kind of, the problems are all kind of the same in a lot of regard. So like, even if it's a challenge, the pattern of the setup will be helpful. Katie. This guy. So again, it's just like, that's like your radius. That's just like some x, right? Where this is 1 and this is 2, right? Does that feel okay? Okay. All right. Yes.
So the way you drew it on the very first graph, could you just do it like that? Or should we?
So the directions for this problem asked us to do all of these steps. That's why I'm doing them all. I'm also trying to help build some intuition. When you're good, you don't need more than this first picture.
Okay.
And eventually that's probably where we'll land, is not needing anything more than this first picture. I think but to build the intuition, to get really comfortable with this, I don't think it's a waste of time to like build out, like think about what these other things have to look like. Is that?
Yeah.
So yes, I agree. By the end, we will not need more than the first picture. And I think often it's all you really want is the first picture. Sometimes the rest of it feels like noise. But until you feel like you understand what's going on, I think doing the other parts is helpful. Is that so far okay? All right. So this point here is just like some xy on that curve, right? The radius is going to be the same as the y coordinate. Everybody agree with that? And if I go back to the original problem, we're told that y equals 2 minus 1/2 x, right? So what that tells me is every point on that curve is going to be x comma 2 minus 1/2 x. So what is my radius then? Radius is the y-coordinate, which in general is going to be just 2 minus 1/2 x. Does this feel, is the pace okay? I'm trying to be really careful and go slow and pause and leave time to think about it and make sure that we're being super clear. Okay. So my cross-sectional area then, it's a circle. It's pi. And then I have my r of x squared. Everybody feel good on how I came up with that? So our volume then is going to be the integral from 1 to 2. Again, we're starting at x equals 1. That's our first slice. We keep slicing until we get to x equals 2. Our area function is pi 2 minus 1/2 x squared dx. Setup is now done. Depending on the directions, you could feasibly type this in your calculator and just ask the calculator to evaluate this for us. Why don't you take your calculator out real quick right now? We'll practice doing that. It's been a minute since we've done it. Again, if I'm doing this by hand, this is what I'm doing after I finish my setup, is I am typing this into my calculator before I start to do any anti-differentiation, because I want to know, did I set this up right, or do I need to go back to the drawing board before I start, doing any integrals? Because I don't want to waste my time, do a bunch of integrals and get the wrong answer and find out, oh, I got it wrong because the setup rather than an algebra mistake or an antiderivative mistake, or, we should have outputted about 4.97. The answer in the back of the book was 19 pi over 12, which matches what we just did. So we know that we've set this thing up correctly, right? Which is awesome. Let's go and now do the integral by hand, because again, just to reinforce and practice some of these ideas. How would we want to do this integral by hand? Okay. So yeah, one way we can do that is begin by foiling out that piece. That's going to be 4 minus 2x plus 1/4 x squared dx. Did you forget the pi?
Yeah.
Easy to do. And because that's a constant, you can just multiply it in at the end after you do the integral. You don't have to go back and put it with the integral. You can just multiply it afterwards. So you could do that. That'll work. So when we do the antiderivative then, what do we get? Great. Mm-hmm. You meant x cubed over 3, I think, right? Okay. So far, so good. So that's going to be, when I plug in 2 then, I'm going to have 4 times 2 minus 2 squared plus 2 to the third over 12. And then we'll have minus 4 times 1 plus 1 squared minus 1 cubed over 12. Is everybody okay with why I was flipping signs there in the second half? Yeah, it just feels neater than doing minus in the parenthesis and then trying to remember to, I'm remembering now I'm going to flip all the signs. All right. So 8 minus 4, and that's going to be 4/3, I think. No, 2/3. Minus 4 plus 1 minus 1/12. Maybe I'll just leave those as 12s, right? 8/12. Okay. So let's see. We have 8, 4, and minus. So that's all goes to 0, right? Then I have 12 12ths and 8 12ths is 20 12ths. Minus 1 is 19 12ths. And we still have that pi from there. So we're done at that point, right? What would have been the other way that you could have could have integrated this? There's another method you could have used. You could use a u sub to do this, right? If we went back to the beginning here, what would the u be? Yeah, 2 minus 1/2 x. Du dx then is just minus 1/2, right? So that would tell us that dx would equal negative 2 du. And we could change our bounds to avoid having to plug anything back in. I know that 2 minus 1/2 times 1 is 1.5 or 3/2. Maybe I'll leave it as 3/2. And then that's 1. So this could be the integral from 3/2 to 1 pi times u squared times negative 2 du. So we're going to take the minus 2 pi out front, and then we're going to swap the bounds, which makes that positive. Is everybody okay there? There's no benefit. There's no penalty for doing one versus the other. I just wanted to remind. It was a good opportunity to review doing this again. But both would work in this case. Most cases in this sort of situation, the u sub would just be used as it makes the algebra a little less messy at the end. And you'll see why here in a second. If I do my antiderivative, I get that. So I'm going to have 2 pi, and then I have 3/2 cubed over 3 minus 1 cubed over 3. So that's 2 pi times 9 over 8 minus 1/3. And if I make a common denominator there, I think I did that right. It's going to be 27 over 24 minus 8 over 24. Yeah, so that's going to be 19 over 24, and I multiply the 2 in. That's 2 pi, or reduces down to 19 pi over 12. So you could do it either way. So when you have bounds, you don't need plus c's, right? Because what happens here is, sure, you could write a plus c, but then you have like a plus c here and a minus c here, and they always just cancel each other out. So we don't even bother writing them when we have a definite integral. But it's not wrong to put them in, but they'll always cancel out. So that's why we don't bother with it. Is that okay?
Yes.
And again, any of these kinds of questions where you're like trying to parse putting this all together, because we've seen a lot of stuff, like ask them. I'm happy to answer them. Someone else is probably thinking the same thing. We're just being too shy to ask. You know, don't be shy. Do we feel okay on this first one? Let's do another, right? I'm going to ask for some help from you guys on this next one. Then we'll see what we can do, maybe solo, depending on how this one goes. Okay. So again, we have y equals 0, that's the x-axis. X equals 5, that's a vertical line. And then y equals the square root of x minus 1. Now, why didn't they give us another x? Like on the previous one, they gave us a left x, like 2 verticals to stick it in between. Why didn't they bother to give us a second vertical on this one? The graph has an endpoint. Very good. Why does it have an endpoint?
Well, it's going from 0, so it can't be negative.
Because you can't square root negatives here. Yeah, so we know that there's an artificial endpoint here when x is equal to 1, right? Because anything smaller than 1, the square root of x minus 1 is going to be negative. Does everybody feel okay with that? All right, so let's sketch our picture then, kind of what's going on. So again, we have boundary here on the x-axis, 1, 2, 3, 4, 5. We have one of those. And then our curve, well, I know that if I plug 1 in for x, I get 0. We already established that's the smallest value that we can plug in, right? If I plug 2 in for x, the square root of 2 is, or 2 minus 1 is 1, and the square root of 1 is 1. And then if I plug, say, 5 in, 5 minus 1 is 4, and the square root of 4 is 2. So that's kind of what our curve looks like. Everybody okay there? So that's our shaded region. It says we're going to rotate about the x-axis. So think about for a moment what this is going to look like in 3 dimensions. Take a minute. If you need to, close your eyes, use your imagination. Think about as you spin that thing along, what's that going to look like? Well, the left end is going to be a circle, right? It's going to look maybe like half of a pill. So like it has like a rounded end, right? I'd think maybe like half a pill, like half a gel cap or something. You guys buy that? Okay. Which way am I going to be slicing? Vertically. Right? Should be hopefully pretty clear. So this is like my x-axis coming through here. Right? Does everybody feel good there? What's the cross section going to look like? I guess I shouldn't put a y in there. Pretty clearly it's a circle, right? All right. So let's pick some x. Everybody's okay? So that distance from the center of our figure, the x-axis, to the outside of the solid is the radius, right? That corresponds to the point x comma y on our figure. What is the radius really? Just the y value, which any point on that curve is just x comma square root of x minus 1. So the radius is square root x minus 1. So our area function should be pi times square root x minus 1 squared. What do you notice here that's convenient? Yeah, the square cancels the square root. Oh, that's real nice, isn't it? Gets me out of having to use a chain rule, or a u sub. All right, so let's calculate our volume then. That volume is integral from what to what? 1 to 5. Excellent. Why not 0? Yeah, very good, because 1 is like the start of our figure, right? That's the first slice we would take. The answer in the back of the book is 8 pi. Take a minute, check it on your calculator. Did we do the setup correct? We're good? Everybody agree? It's a nice little check, isn't it? The setup's the hard part. That's the part I really care that we are making progress on. All right. So no need to u sub this one, right? That's not even a consideration. So let's just do our antiderivative. Again, we ignore the constant. What's the antiderivative here? Just shout them out when you have it. Yeah, there you go. Do some showing off. Let everybody know. It's like, I know what's going on. I'm not paying attention. So far, so good. Okay, so that's 25 over 2 minus 10 over 2 minus 1 over 2 plus 2 over 2. Everybody agree? So that's going to be 16 over 2, or just 8 pi, which is what we wanted. All right. Actually, I take it back. We're going to do one more together, because here they've changed. They did something different. We should probably do this one together before I ask you to do one kind of soloed. Oops, I don't know where that just put that at, but not where I thought it would. That's so teeny. All right. Questions so far? Is this going okay? Does it feel better than when you watched it the first time? Okay, good. That's my hope. I knew this was going to be hard, but I was planning on doing a second day anyway, so I'm like, well, it'll go better if you've at least have the idea here. All right. What do you notice right away that's different? Yeah, and look at the function that's defined. It's defined x equals instead of y equals, right? So everything is going to be kind of reversed. Let's keep that in mind when we think about what our picture is going to look like. So we're stuck between x equals 0. What's x equals 0? The y-axis. And then y equals 9. Oh, I didn't give myself enough space. I'll just do that. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Now, how am I going to graph x equals 2 square root y? Well, you could do that. What if instead we just think about making like a yx table, right? So what's the smallest y I could possibly pick? 0, right? I can't pick negative y's because the square root, right? And then maybe I'll pick y to be 1. If I do that, x should be 2. And then maybe pick y to be 4. If I do that, x should be plug 4 in. The square root of 4 is, and then times 2 is. So 4 would be my next one. So 1, 2, 3, 4. 1, 2, 3, 4. And then maybe I'll pick 9 for y. And what would x have to be then? 6 is correct. 1, 2, 3, 4, 5, 6. You feeling okay with how I generated the picture? Okay. And then we're going to spin about the y-axis this time instead of the x. Right? Because that's what the direction says about the y-axis.
Why don't color because it's the y?
Why did I color? Well, it said it needs to be between these lines, right? Needs to be between this, this, and this, which is the yellow part that I shaded, right? So those are the boundaries. So again, I'm having to, it's not always just going to be straight down to the x-axis. It means like in between this stuffs, right? Does that make sense? Okay. All right, let's think about what this thing's going to look like in 3 dimensions. Close your eyes, try to imagine. Again, we're spinning about the y-axis this time, so it's like one of these rather than one of those. What's it look like? Basically the same as the last one, right? It's just facing a different direction. Everybody agree? Well, it's like the y-axis coming through it. This time, are we slicing vertically or horizontally? Horizontally, right? It's okay. The amount of students that confuse those two, vertical and horizontal, when they're not, like it happens all the time. Okay, great. So I want a helpful hint. If you're slicing perpendicular to the x-axis, like we did in the previous problems, right, where our slices are perpendicular to the x-axis, you'll want to write everything in x, and you'll be integrating with respect to dx. If you are slicing so that you are perpendicular to the y-axis, you'll want everything in terms of y's, and we'll be integrating with dy. Okay? It's the easiest way to think about it. Just however you're doing the slicing, the axis you're slicing perpendicular to, that's what you want your variables, or that's the variable you want in your integral. All right. So again, no surprise here. All right. Our cross section is just going to be a circle. So this would be like a radius, correct? Everybody agree with that? So the radius here, if this is just some y coordinate we've chosen, the radius is just really the x coordinate, right? So if I look at this, I'm going to be using this function, right? Because that's the function we're relying on. The x value is always going to be 2 square roots of y, and the y is just y, right? That's what the function is saying. And that's how we plotted the points on there, right? We chose a y and then found the x by plugging it into 2 times the square root of y. So what's the radius then in this case? Yeah, so my r of y is 2 square roots of y. So my area function is in terms of y's. Does everybody feel good? What's that simplify down to? No. 4 pi y, yeah. Just doing a little quick check. Let you make the mistake and then we'll correct it. All right. So our volume then, we're integrating from what to what? 0 to 9. Why 9? Yeah, because we're going respect to the y-axis. So we're integrating along the y-axis. So we're starting 0 and ending at 9. Everybody catch that? Very common mistake to still put x's for your bounds. Have to be careful, right? If it's integrating with y, everything is a y. And then we have 4 pi y dy. Should be a really easy antiderivative. So what do we have here? We have 2 pi 9 squared minus 0 squared. All right. Let's try 7. What was I doing on the right in red there? Yeah, I was finding where the two things intersected, right? To find the intersection, should I just set the equal to each other and solve for x? Why did I discard x equals -1? Yeah, because I know it has to be greater than 0. Everybody feel okay with that? All right, what's this thing look like now? You guys see what I'm drawing or not really? So you're going to have like an opening in the middle, right? The opening in the middle is going to like come down to a point. It's like a cone with a Hershey kiss cut out of the inside of it. So think about like a cone, and think about like a Hershey kiss taken out of the inside of the cone. So it's like a hollow Hershey kiss in the middle of it. Does that make sense? That kind of, it's like, I got it. I can see it now. So what's that cross section going to look like then? If we slice here, you're going to have like an empty spot. There's a hole in the middle of the cross section. Right? So you had a cone, right? Like you had a cone, and then you've taken like a Hershey kiss out of the middle of it. So that shape missing from the middle is like a Hershey's kiss. So if you start chopping this way and you look at what you chopped, there's going to be a missing circle from the middle, from the Hershey kiss. Does that? So if we pick some x, we're going to have an inner radius, right? And then we're also going to have an outer radius. Everybody kind of see that? Because our area is going to be pi outer radius squared minus pi inner radius squared. That'll give us the shape of the, right? That's the big circle minus the little empty part from the middle. This shape is called a washer. Those of you that have like done anything with building anything knows what a washer is, like with screws and stuff. Not like a washing machine, not somebody that does your laundry, but like the part. So let's look at how we're going to compute this then. That's Ri, correct? So that part is on the curve here. Correct? Everybody agree? So that's x comma x cubed. Since Ri is clearly a y coordinate, Ri should be x cubed. So that's Ro, R outer. That's x comma x. So R outer is just also the y coordinate, x. Does that feel okay on what I've done there? To find the inner and outer radii? Isabel?
For the y plus x, is it just x comma x?
Yes. Because R outer is a y coordinate, right? So I need to rewrite that y coordinate in terms of x.
Yeah.
And since it's y equals x, well, it's just x comma x. Katie. Okay. Go for it. Do the best you can.
So why is it the drawings?
Right. The y coordinate is the radius for both the inner or the outer, but it's to different functions, right? All right. So if we plug these in then, our volume is the integral from 0 to 1 pi, and our outer is x. Our radius inner is x cubed. And then we should have a dx then still at the end. You guys feel okay with the setup there? So do our antiderivatives. You okay with that I factored the pi out, I hopes? Right? You see that I did that? So what do I have? I have 7 over 21 minus 3 over 21. So 4 pi over 21. Bless you. Okay. I want to jump ahead, and we just have a few minutes left, but I want to just kind of get to the setup of one of these guys that has not an axis that we're rotating about. So I'm going to pick this one because it's well, the shape is rather straightforward. So we're between here, we'll call that 1. And then we're rotating about then that line. What are we going to get here? Right, it's like something like that with a tube cut through the middle of it. So our radius our Ri is going to be there. And our RO would be there. Now, this is quite nice because the Ri is just a constant. What's the distance? 1. What's the RO going to be? No.
I just guessed.
Yeah, so let's think about it here. This distance is, that distance is 2, correct?
2 minus.
That distance is x. So RO would be 2 minus x. But what variable should we be integrating with respect to? Y, correct? Because we're spinning about a vertical. So that's like x comma y cubed, but we don't want it that way. We want cube root y comma y, right? Right? Because that's the same thing as saying cube root y is equal to x, right?
Oh, yeah.
So we integrate from 0 to 1 of pi 2 minus cube root y squared minus pi 1 squared dy. I'm stopping here because clearly we're over time, but try to work on some more of this tonight, guys. There will be hard ones. It is not easy. Be patient, go slow, try to draw good pictures. Your ability to draw a decent picture here pays huge dividends. Okay? Do your best, guys. What's up?
You ain't touching me in today.
I hope so.
Oh, how